If you've had a class in algorithms, then you have seen how to design an algorithm for computing shortest paths in graphs. In this problem, the input is a directed graph, an object that looks like this, where there are n vertices, okay? And each of the vertices are connected by m edges or links, and each of the edges has a weight, which is an integer. Okay. The goal of the problem is to find the shortest path between two vertices, between S and T. So in this example, here's an example of a path that goes from S to T, and the length of the path is just the sum of the weights of all of the edges along the path. So this is a really basic question. It's one that people have studied for a very long time. And in the last couple of years, there's been some really amazing progress on this question. And we now know how to give nearly linear time algorithms for this problem, even when the graph has negative edge weights. And that's the algorithm that I want to discuss in this video. I'm going to start by reviewing some really basic algorithms for this question. But if you want to just jump directly to the new ideas, then you can skip ahead to this time point in the video. So let's start by first discussing Dijkstra's algorithm. Dijkstra's algorithm is a basic algorithm for this problem that runs in almost linear time as long as the edge weights are all non-negative. The goal is to compute the distances of all of the vertices in the graph from S. To do this, we start by setting all of the vertices to be undiscovered and set the distance dv to be infinity for all v that is not equal to S, and set ds itself to be 0. Okay. And then in every step, while there's an edge that goes from a discovered vertex to an undiscovered vertex, you set you pick uv to be the such an edge that minimizes the quantity du plus wuv. Okay. And then you set the value of dv to be du plus wuv and mark v as discovered. Okay. Now I'll make the intuition for the algorithm clear by showing some pictures. So here's what the algorithm looks like if you run it on this input graph. Initially you set ds to be 0, and all other d values are infinity. And then you look at, we're sort of blowing up a bubble, okay, which is the bubble contains all of the vertices for which we've already set the shortest path distance correctly. Initially that set contains just S. And then in each step we look at the vertex that is cheapest to discover. So in this case, we could discover A at a cost of 2 or B at a cost of 12. So it's better to discover A. So we discover A and set its cost to be 2. And now we include A in the bubble of discovered vertices. In the next step, the cheapest vertex to discover is E, which we can discover at a cost of 3. Okay. So in this way, in every step, we expand the bubble to find the next vertex that's cheapest to discover. Okay. So that's the entire algorithm. Now, to argue that the algorithm is correct, you prove it by induction. The point is that you claim by induction that the d values of all of the discovered vertices are correct. And given that that's true, it's true initially. If you've at any point discovered some new vertex v and are about to mark it as discovered, we need to prove that the value it's being given is in fact the shortest path distance. Okay, but that's true because if it was not the shortest path distance, if there's some other shorter path that goes from S to V, then this vertex V prime, which is the first vertex on the path that goes outside the discovered set, that one would be cheaper to discover than V. So the dv value we're assigning here must be correct because if not, then there would be a vertex v prime that would be cheaper to discover at this point. So that's the idea of the algorithm. And in this proof, we use the fact that all of the edge weights are non-negative. And if that's not obvious, you should think about exactly where we use that fact. So that's Dijkstra's algorithm. In order to implement Dijkstra's algorithm efficiently, we need a data structure called a heap, which is a very simple data structure. What it allows us to do is maintain the set of distances in the graph and manipulate them efficiently. So what is a heap? It's a collection of all of the vertices in the graph along with their distance values. And they're maintained in the shape of a binary tree, where the invariant is that every vertex has value that is at most the value of its children. Okay, so S here has a distance 0, then A and B, which are its children, have only larger distance values. Okay. The operations that the heap supports are, you can delete the minimum vertex from the heap while maintaining this invariant. And to do that, you just replace the root with the last node, like so. This now violates the invariant that every vertex has a value that's less than or equal to its children. But you can now swap this vertex with the smaller child repeatedly until this property is restored. You can also reduce the value of a node. So if you have a node in this tree and you want to reduce its value, you can simply bubble it up. So for example, in this example, I've reduced the value of C from 14 to 2. And then I can just bubble it up by swapping it with its parent until the invariant is restored. Okay. So those are the kinds of operations you can do with a heap. And each of those operations takes order log n time. Okay, so it's very fast. So given this data structure, we can now implement Dijkstra's algorithm very efficiently. The way we do that is, as before, we start by setting dv values of all vertices to be infinite, except for s, which we set to be 0. And then we make the heap by adding all the vertices with their d values. And while the heap is not empty, we first delete the vertex at the top of the heap, the one with the minimum d value, at this point. And then we explore all of the edges coming out of that vertex. And for each edge coming out of that vertex, if dv is bigger than du plus the distance from u to v, this means we found a shorter path to v. Okay, so then we update dv to be equal to du plus the weight of the edge from u to v. Okay, this algorithm now has running time that's order n plus n log n, and that's because every time we pop out a vertex from the heap, we explore the edges coming out of it. And this means that every edge in the graph can be explored at most once in this way. Okay, so that gives you a bound on the running time that looks like this. So here's an example of an execution of the algorithm with the heap, and a picture of the heap. So at some point, let's say we're at this stage, and we've just popped C off the heap and assigned it the value d value 7. We now look at the edges coming out of C. There's 1 to f and g, and we reassign their d values. We assign f8 and g11 and restore the heap before continuing. Okay, so that's how Dijkstra's algorithm works with a heap. Throughout my description here, I've just said how to compute the length of the shortest path, okay, without actually describing how to obtain the shortest path. But it's easy to modify the algorithm I've described here to generate the shortest path tree, which describes the shortest path from S to every other vertex in the graph. Okay, and I'll leave it as an exercise for you to figure that out if you don't see how to do it already. Okay, so how can we handle negative edge weights? Until the last few years, the only known algorithm for this was the classic Bellman-Ford algorithm. Now, before I describe that algorithm, I should point out that when you have negative edge weights, if the graph has a negative cycle that's reachable from S, then the distance, the shortest path from S is not really well defined, because it might be possible to go from S to this negative weight cycle and just go round and round the cycle many, many times, getting a very, very small distance, as small as you want, before moving on to the target vertex T. Okay, so for this reason, it makes sense to assume that the graph does not have a negative cycle when talking about this problem, or give an algorithm that either finds a shortest path or finds a negative cycle in the graph. And throughout this video, for simplicity, I'm just going to take the easy route and assume that there are no negative weight cycles. Although all the algorithms and ideas I'm going to talk about can be modified to actually discover when there is a negative cycle in the graph. Okay. So let's just assume that there are no negative cycles in the graph. Then the Bellman-Ford algorithm is very simple. It looks like this. You set dv to be infinite to start out with, and ds to be 0. And the algorithm proceeds in n-1 rounds. And in each round, you run over all the edges uv and update that edge according to this rule. Okay, so if dv is bigger than du plus wuv, meaning that there is a new shorter path, then you change dv to be du plus wuv. Okay, so that's the algorithm. And here's an execution of that algorithm. So while you're running the algorithm, at some point you see the d values change, and sometimes they don't change. But you keep running this until the d values, hopefully at some point, reach their correct value. Now, why does this algorithm work? Well, the analysis is simple. So the idea is, suppose the shortest path from S to V, the one that realizes the shortest path distance, is this one that goes from S to V1 to V2 all the way up to Vj and then to V. And its length is this expression. Then the observation is that in the first round, when I is equal to 1, dv1 will be set correctly. That's because dv1 must be equal, the distance from S to V1 must be equal to the length of this edge, right? This must be a shortest path to just V1. Otherwise, you'd obtain a shorter path to V. Okay. So dv1 is set correctly after I is equal to 1. Okay, because the algorithm finds that shortest path in the first round. And after I is equal to 2, dv2 is set correctly. Okay. Because it's already found the shortest path to V1, and in the second round it will discover the shortest path to V2, and so on. So after the J plus first round, it will have discovered the shortest path to V. Okay. So that's the algorithm. It's very simple, and the running time is basically order m times n. All right, so that concludes my review of the old classic algorithms. And now let me move on to the interesting part. I'll talk about the new algorithm. So what does the new algorithm accomplish? It gives an algorithm for computing shortest paths, even when there are negative edges, in time that's almost linear in the number of edges. Okay. So if the edge weights in the graph are at least minus t for some parameter t, the algorithm has running time that looks like order m plus n times some expression that's polylogarithmic in n and t. One interesting fact about this algorithm is it's a randomized algorithm, and I think it would be very interesting to find a deterministic algorithm that achieves the same parameters using similar ideas. An extremely useful idea is that it's enough to find a potential function on the vertices of the graph with the following nice property. Suppose we could find a function phi of all the vertices of the graph that maps each vertex to a real number, such that for every edge uv of the graph, we have this inequality, that the weight of the edge plus phi of u minus phi of v is greater than or equal to 0. Then we're in great shape. The reason is we can now run Dijkstra's algorithm using the edge weights theta of uv, which is defined to be the weight of the edge plus phi of u minus phi of v. And all of these quantities are promised to be non-negative, so Dijkstra's algorithm will find the shortest path from S to T in this graph. And Dijkstra's algorithm is fast. It will run in almost linear time. And moreover, the claim is the shortest path with the new edge weights is also a shortest path with the older edge weights. And that's because if you look at the length of the path, the length of any path, it's under the new edge weights, it's equal to phi of s minus phi of t plus the length of the path under the old edge weights. Okay, so every path from s to t has been shifted by exactly the same amount using the potential function. And therefore, the shortest path remains a shortest path. So the shortest path we find using Dijkstra's algorithm is correct. Okay, so that's a really nice observation. And where can we find such phi? Well, there's one very natural way to find phi, which is set phi of u to be the distance from S to U, the shortest path distance from S to U for some arbitrary vertex S. Okay. And that would work, except for the fact that we don't know how to compute shortest path distances. That's the problem we're trying to solve in the first place. Okay. But at least it gives you the power to say that we can now, as long as we find shortest path distances from some arbitrary vertex, then we're done. Okay. And the reason that works is because, if you set phi of u like this, then you see you have this inequality because the path that goes from S to U and then from U to V can only be longer than the shortest path from S to V. Okay, and that inequality is the same as what we wanted up here. Okay. So this is the framework we'll adapt from now on. Instead of finding shortest paths, we'll look for a potential function phi that satisfies this kind of inequality. Okay, the next iteration on this idea is that it turns out it's enough to have the following approximate version of these inequalities instead, and that's still good enough. So instead of asking for the phi of u from before, it's enough to find phi of u such that this inequality holds for every edge uv. Okay, 3n times the weight of uv plus phi of u minus phi of v should be at least minus 2. Okay. That's a little bit of a weaker inequality than we were asking for before, but it's still good enough because we can now set theta of uv to be the maximum of 0 on the left-hand side here. Okay. In other words, if we see if the left-hand side is negative, then just set it to 0. Now, the reason this works is that if you consider the length of any path under theta, its length can be expressed as kappa plus the sum for every edge of the left-hand side over here, where kappa is a number between 0 and 2k. Okay, this is the error you get by replacing the edge weights with 0 sometimes. And some of the edge weights become replaced with 0. Okay, so this kappa is between 0 and 2k. And that means that the length of the path looks like kappa plus phi of s minus phi of t plus 3n times the old length. All right. And so the point is that now if you have two distinct paths from S to T in the original graph under W, and they have distinct lengths, so one of them is shorter than the other, then the worst thing that could happen is that the shorter one, its length gets increased by 2 times n, and the longer one has the same length as before. But because their lengths were distinct under W, meaning that they differed by at least 1, once you multiply the edge weights of W by 3n, they now disagree by, they differ by 3n. So the shorter one cannot become longer than the longer one under theta. Okay, so it's still good enough to compute the shortest paths under theta. Okay, so that's a nice idea. So given those ideas, we'll obtain our final algorithm by implementing the following step. Okay, this is the heart of the algorithm. So the key step will give a nearly linear time algorithm, which when given a graph with edge weights zeta that satisfy that zeta is an integer whose value is at least -1. Okay, so the only negative weight edges are those whose weights are -1. And zeta also satisfies another very strong condition, which is that every cycle with k edges has weight at least k under zeta. Okay. So these are the two properties that zeta is promised to have. And we'll give an algorithm that, given such a zeta, can find a potential function phi that makes all of the edge weights non-negative. Okay. So let me explain why this algorithm is extremely useful. If you had such a subroutine, one that implements this step, then we can do the following. We start with edge weights W, which are all guaranteed to be at least some parameter minus t. Let's set zeta of uv to be this quantity, the ceiling of 3 times W divided by t plus 1 plus 1. Okay. Now, this zeta satisfies the two properties that I described here. It's at least -1 because by the choice of the ratio here, this first term here is at least -2. It's always at least -2. And then we increased the weight by +1. So all of the zeta values are at least -1 and they are integers. Okay, that's the first property. And for the second property, you see that if you take the sum over any cycle of the zeta values, then the value can be expressed as at least k plus the quantity in here, right? That's because the k comes from the k edges of the cycle. And then if we get rid of the ceiling, we can only get a value that's smaller. Okay, but this sum is non-negative because we're promised by assumption that there is no negative cycle in the graph. There is no negative cycle in the graph. Okay, so the sum of the weights on any cycle is at least k if the cycle contains k edges. All right, so this weight function zeta satisfies both conditions. So we can now apply the subroutine to compute the phi satisfying this inequality, but that translates to this inequality. Okay, because if I replace zeta with this quantity, that can create an error of at most 2, right? 1 because of this, I've removed the ceiling function, and an additional 1 because I've ignored the +1. Okay, so I get this inequality, and once I have this inequality, you see that if I consider the potential function tau of u, which is t plus 1 over 3 times phi of u, then I get w of uv plus tau of u minus tau of v is at least -2 over 3 times t plus 1. And that's progress, because we started with the assumption that w is at least minus t. And using the subroutine, we now got a new weight function, which is at least minus roughly 2t over 3. Okay, so it's closer to being non-negative. That's a lot of progress. So if we now repeat this, we start. So here's the final algorithm. So let's start by setting all weights to be 3n times the original weights, and apply the above process, roughly log of n times t times, until the weights we obtain are all at least -2. Right? In every step, the weights, the negative weights, decrease in magnitude by a constant factor. So after log n times t steps, they will decrease all the way down to -2. At that point, as we've discussed before, we can use Dijkstra's algorithm with this weight function to find the shortest path. Okay. So this scheme eventually gives us a linear time algorithm for finding shortest paths under W. All right, so those are some clever ideas, and they've reduced the problem now to this situation. It's a very nice, simple situation where we have that the only negative edges are those that have weight -1, and every cycle with k edges has weight at least k. Okay, so now let's try to give an algorithm that achieves this goal. Okay, let me explain some really nice consequences of the assumption about cycles. Let's define, given a weight function zeta satisfying these two assumptions, let's define zeta greater than or equal to 0 to be the weight function where we take all of the negative weights and set them to be 0. Okay. That's this weight function. And let's define these two balls so that this ball, the forward ball of radius r around a vertex u, is the set of vertices v that you can reach within. It's a set of v that are within distance r under the non-negative weight function, under this weight function. And the reverse ball is the set of vertices such that the distance from v to u is at most r under the same non-negative weight function. Okay. And let's imagine now, remember our goal is to compute a potential function phi of u satisfying this inequality, and as I said before, it's enough to set phi of u to be the distances from some vertex s in the graph. So let's add a dummy vertex s to the graph and connect it to all of the vertices u with an edge of weight 0. Okay. Then here's a key lemma that's very useful. It says, suppose you have that for every u, both of the balls, both the forward and the reverse ball of radius delta over 2, have size bigger than n over 2. So say all of the balls of radius delta over 2 are big. They're bigger than n over 2 in size. Then the claim is that there is a path that every shortest path from S to V under the weight function zeta uses at most delta edges, uses a few edges. Actually, I think there's a typo. This should say delta plus 1 edges. Okay, but anyway, the point is that if all of these balls are big, then I want to prove to you that every shortest path must be short, must have a small number of edges. Okay. And why is that? Well, so consider any shortest path from S to V. So let's say you have this red path, which is the shortest path. Now, there is an edge that goes from S to V directly with cost 0. So the length of this red path must be less than or equal to 0. Okay. On the other hand, the assumption about all of the balls being large implies that there is a vertex that is in the intersection of these two balls. Right? These two balls are both of size at least, they're bigger than n over 2, so they must intersect. And because they intersect, there's a path that goes from V to this intersecting vertex, the vertex in the intersection, and then to u, whose total length is at most delta over 2. Okay. So there is such a path in the graph. And this gives us a cycle, this one, whose total length is delta, is at most delta. And by assumption, any such cycle can have at most delta edges. Okay, so this cycle can have at most delta edges. And that means that this path here can have at most delta or delta plus 1 edges. It doesn't really matter. Okay. So that's really powerful. If every ball in the graph is large, then every shortest path involves a few edges. And that's extremely useful because you see, the way we designed the Bellman-Ford algorithm, when we talked about it, the reason we needed to iterate it n times here, okay, is because there are shortest paths that involve n edges. That's the only reason we need to run it like n times. If we knew that all the shortest paths involved only k edges, for example, then we could just iterate this algorithm. We could just do k rounds here, and the algorithm would find all the shortest paths. Okay. So the running time of this algorithm can be improved if we know that all shortest paths involve few edges. In fact, it's a little bit stronger. We can modify the algorithm with not too much work to obtain the following algorithm. Okay, so here's the algorithm. But ignoring the algorithm for a second, here's what we can prove about it. We'll show that if you're guaranteed that for every v, there is a path from S to V that's the shortest path using at most eta of v negative edges, then the running time of this algorithm can be bounded in terms of this parameter eta of v. Okay, in fact, it's the sum over all v of the degree of v, namely the number of vertices touching, the number of edges touching v, times eta of v plus 1. Okay, so if you know that every vertex has a shortest path from S to V that gets there with few negative edges, then the algorithm is fast. Okay. So what is the algorithm? Let me describe it. So the algorithm combines Dijkstra's algorithm and the Bellman-Ford idea. So just like in Dijkstra's algorithm, it starts by maintaining a heap. So we have initially dv set to be infinity for every v that's not equal to s, and ds is set to 0. Then we make a heap with all of these vertices. And then we start running the algorithm. We have this set A, which we initially set to be the empty set. And while the heap is not empty, this first part is basically Dijkstra's algorithm. Okay, where we run Dijkstra's algorithm just using the non-negative edges in the graph. Okay, so just consider only those edges whose weights are non-negative. I actually think in this algorithm there's another typo. I need that to consider all the weights which are actually non-negative, not just greater than or equal to 0, but not just greater than 0, but greater than or equal to 0. So this is just a description of Dijkstra's algorithm using the non-negative edges of the graph. But every time you take off a vertex u from the heap, you add u to a. Okay. And then in the second phase, you do something along the lines of Bellman-Ford, where you run over all of the edges coming out of the set A. For every u in A, you run over all the edges coming out of U, and run over all the negative edges and do an update along those edges, just like in Bellman-Ford. And for every vertex V, whose distance d value is actually changed in this process, you add V back onto the heap. And if if the heap is not empty, you go back to this step and repeat the process. Okay, so that's the algorithm. Now, what's going on in the algorithm? Well, suppose you have, so let's try and analyze the algorithm. Suppose you have a vertex V, and the shortest path to V looks like this. It has some non-negative edges and then some negative edges along the shortest path. The claim is, after you run the first step, this part, then all of the vertices up to this point, the point right before the first negative edge, they will get the correct d values. Okay, because when you run Dijkstra on this part, it will correctly compute all of the d values up to here. And that's because the proof of Dijkstra works. Okay, so whenever you consider a v here and you're about to set its d value, there cannot be a shorter path that only involves non-negative edges. Okay, or Dijkstra will use a different v prime at that point of the algorithm. Okay, so this finds the shortest path among all of the non-negative edges. So these vertices will get the correct d values. And then in the next phase we run step 2 here, and at that point this vertex will get the correct d value. Okay. Then the next time we run Dijkstra, all of these vertices up to the next negative edge will again get the correct d values, and so on. So that's the idea of the algorithm, and I'm going to leave out the details, but I hope you're convinced about the intuition for why it works. Okay, so we're interleaving Dijkstra and Bellman-Ford. Every run of Dijkstra takes care of an interval of non-negative edges along the shortest path, and every run of Bellman-Ford handles one negative edge. Okay, why is the running time this expression? Well, once a vertex gets the correct d value, it stops participating in this algorithm. Okay, the only vertices that participate and re-enter here are those whose d values are changed in this step. Right? So how many times does a vertex participate in this part of the algorithm? It's the number of rounds here before it gets the correct d value. And after it gets that, and that's bounded by eta v plus 1. And after eta v plus 1 rounds, the vertex no longer participates. And every time it does participate, it contributes degree of v to the running time of this algorithm. Okay, so that's why the running time looks like this expression. So we've already talked about how if the graph is very strongly connected, you know, all the balls are large, then every shortest path in the graph has a small number of edges. Okay, and that would make the algorithm we just described work. But what about the other extreme? You know, what if actually the balls are not large? You know, so let's think about some extreme examples along that direction. For example, what if there's a vertex V which simply has no incoming edges? Okay, so it's unreachable from any other vertex. Okay, then certainly the balls are not large, or one of those balls is not large. But then there's a very simple solution here. We can just compute phi u, the potential function we're after, for all the other vertices in the graph, and then set the value of v, the potential function, so that we have this inequality. Okay, you can do it by setting its value to be this quantity. Okay, and computing this phi of v from the other phi values is efficient. Okay, so doesn't seem too hard. And in the same way, you know, if you have a v which has no outgoing edges, you can do something similar. Compute the phi values for everything else, and then you can set the phi value for this vertex. And more generally, if you have two sets of vertices v1, v2, such that there are no edges going from v1 to v2, okay, no edges going from v1 to v2, then you could compute phi on v1 and phi on u2, phi1 on v1 and phi2 on v2. And then you can combine those phi values to get a global phi, one that works for all of the edges in the graph. So these phis work for the vertices in V1 and the edges that are contained there, and the vertex phi2 works for the vertices V2 and the edges that are contained there. The only remaining edges is the one that goes from V2 to V1. But you can easily handle all of those edges by shifting one of the phis. For example, shifting phi1 by this quantity. Okay, that will handle all of the edges that cross from V2 to V1. So the upshot is, if you have two sets of vertices where all of the edges between them go in one direction only, then you can easily combine the underlying potential functions to obtain a new potential function. Okay. So that's very nice. So sort of, if you have a graph which is very strongly connected, then we have an algorithm that works. It's the BFD algorithm we discussed before. And if you have a graph that's not very strongly connected, in the sense that there are such partitions into vertices, then you can recurse on the parts of the partition and somehow combine the results to obtain the desired potential function. So it seems like we're starting to get all cases covered. Okay. So let's now try and use these ideas to design an algorithm. So here's a first kind of cut at designing an algorithm. So let's say throughout we have some parameter delta, which is an upper bound on the number of negative edges on shortest paths from S to V. Okay. Now in the first case, if you have the case that for every vertex, all of the balls we talked about of radius delta over 4 are big. Okay, that's one nice case. In this case, the diameter of the graph we're working with the non-negative edges, right, is small. So by the lemma we discussed before, it means that every shortest path from S to V has at most delta over 2 edges. And so we can just recurse. In this case, we know that actually the parameter delta is a weak upper bound. There's a stronger upper bound of delta over 2. And we can actually recurse on the graph with that parameter instead. Okay, so that's good. You cannot do that recursion too many times, right? Because we reduce delta by a factor of 2. It starts out as being bounded by n. So after log n such recursive steps, the algorithm must terminate. On the other hand, if there is a vertex u where one of these balls, say this one, is small, then you see intuitively you have the balls are not expanding. The ball is not expanding very fast. So intuitively there must be some radius for which the number of edges going from the ball of that radius to the complement is small. Okay, the ball going from the edges crossing from inside the ball to outside must be small. And if that's the case, let's say just for now that there are 0 edges going from inside this ball to outside this ball, then we'd be in good shape because we can now compute phi on the ball and compute phi on the complement of the ball. 2 different potential functions that work, one for inside the ball and one for outside the ball, and then combine them, as we discussed before, to get a function phi that works for the entire graph. Right? Because if we know that all of the edges only grow from outside the ball to inside the ball, then we can combine potential functions using the approach we discussed before. Okay. And if there are some edges, but not a lot, going from this ball to outside the ball, then we can first combine this, as I described here, to get a global potential function, and then try to resolve the vertices that go in the wrong direction, the vertices that go in this direction, because under this potential function, those the edges that go in that direction, under this potential function, these edges going from inside the ball to outside the ball are the only ones that can have negative values. Okay. So we can run the BFD algorithm to try and address those edges. Okay. Now, the problem is maybe this intuition doesn't make that much sense, because the fact that the ball is not expanding doesn't mean that the shortest paths do not intersect the boundary of the ball a lot. For example, you could have this picture, right? You could have a ball and it doesn't expand a lot, so there are not many edges on the boundary, but it could be that some shortest path sort of goes along the boundary and crosses from inside the ball to outside the ball many, many times. And that would make the BFD algorithm take a long time, right, to compute on that shortest path. Okay, but nevertheless, let's try to fiercely move forward and make this approach work. So here's a slightly more fleshed out approach to doing the algorithm. So let's say we're in the second case and there's some u where the ball is small. So here's the most natural thing to do. Just pick a random radius r from 1 to delta over 4. Okay. And now you see that if you have an x that's inside this ball, the ball of radius r around u, then y must belong, if you have an edge xy, then and x belongs to this ball, then y must belong to the ball of radius r plus the cost of going from x to y, the edge weight of going from x to y. So in particular, the probability that this edge is on the boundary, okay, crosses from inside the ball to outside the ball, is bounded by the weight of the edge divided by delta over 4, right? Because we can only get unlucky if the r that we pick is exactly in the range that's in between these two parameters. Okay. It contains x but does not contain y, and there's a short interval of parameters where r can have that feature. Okay, and so that gives you a bound on the probability that any edge is cut by this process, by this random ball. And because the shortest path distance from S to V is less than or equal to 0, and the negative edges on the path from S to V contribute at most minus delta, right? Because they're at most delta negative edges by assumption. The non-negative edges can contribute at most delta, right? So the total non-negative edge weight is at most delta. And that means the expected number of edges cut along this path from S to V is bounded by a constant. Okay, that's because if you take the total length from S to V, the total non-negative length from S to V, that's at most delta. That's at most delta by this argument. So with this choice of parameters, you see that in expectation, you only cut a path, the shortest path from S to V, in a constant number of locations. And that suddenly makes the BFD algorithm very efficient. Right, so typically we just need to run the BFD algorithm for a constant number of rounds before it finds the shortest path to be. Okay, so those are some very clever ideas. So this suggests, putting all of these ideas together, we get the following approach. So if we're the case that all of the balls are large, then we just recurse with a smaller parameter of delta. If, on the other hand, some ball is small, then what we do is we pick a random radius r and pick the ball of radius r around u. And then we find a potential function inside the ball recursively and a potential function outside the ball recursively. then we resolve all of the edges that go from outside to inside, as we discussed, okay, to obtain one potential function that works inside the ball, outside the ball, and works for the edges going from outside to inside. And finally, we run the BFD algorithm to resolve the edges that go from inside to outside the ball. And the number of such edges going from the inside to outside is going to be small along every shortest path, by the argument we made on the previous slide. Okay, so that's the overall approach. So that leads to, so here's a high-level scheme for an algorithm. So in the first case, all the balls are large. We just recurse to the parameter delta over 2. In the second case, there's some u for which the ball is small. Then we pick r at random and recursively compute phi on the ball and the complement of the ball. Combine the two phis to get a phi that works for the edges going from the complement into the ball, and then use BFT to fix the edges going from inside to the outside. So that's the idea of the algorithm. Now, if the other kind of ball is small, then we do the symmetric thing. Okay. It's the same ideas. So that's a very high-level approach to solving the problem. All right, so that there are many details that I haven't yet fleshed out, which will cause us some headaches. So let's start discussing them. The first is, how do we even tell which case we're in? Right, how do we compute the size of all of these balls? And that itself might be very expensive. Okay, so that's the first problem. And to resolve that, we'll use random sampling. So here's the idea. Let's pick k, which is roughly order log n, vertices uniformly random from the entire graph. Okay, so pick k random vertices from the graph and compute all of the distances from these vertices to all of the other vertices, and from the other vertices to these vertices. You can do that with order k runs of Dijkstra's algorithm. Okay. With a single run of Dijkstra's algorithm, you can compute the distance from Q1 to all the other vertices. And then you can also compute the distances from the other vertices to Q1 by reversing the edges and again using Dijkstra's algorithm. In these computations, we're only using the non-negative edge weights, right? Because we're computing the distances under the weight function zeta greater than or equal to 0. Okay, so the execution of this first step is almost linear time. So now that we have all of these distances, for every vertex, we can compute whether its balls are big or small with high probability. Because for every vertex u, we can just check whether this ball, the ball radius delta over 4, contains 0.6 fraction of all the q's or not. Okay. Once we have these distances, for each vertex we can check how many of the q's fall within this ball. And if both of them contain 0.6 fraction of the q's, that means with high probability, okay, with probability something like this, both balls must be large, must be at least 1/2 of the entire space. Okay, that's just a standard Chernoff bound argument, right? If we sample log n vertices, if these balls are small, it's very unlikely that you will get 0.6 fraction of the samples inside the balls. Okay, so in this case, we recurse with parameter delta over 2. So in this case, we know that all shortest paths are of length at most delta over 2, and we can safely recurse. On the other hand, if there's some u for which the ball is small, which is indicated by the fact that this ball contains at most less than 0.6 fraction of the q's, then this means that with high probability the real ball has size at most 0.7 times n. Okay. In that case, we pick R uniformly at random, like before, recursively compute phi for the ball and the complement of the ball, combine them to obtain something that works for all of the edges that go from the complement into the ball, and finally run BFT to get something that works for the edges that goes from inside the ball to outside the ball. So that's our second attempt at writing an algorithm. And the problem with this approach, it almost works except for the analysis of the running time. The execution of a single round of this algorithm is almost linear, nearly linear. That's not a problem. The problem is that one of the recursive calls here, this ball is guaranteed to be small, and that's okay. But it might be very small. And in that case, this ball, for example, might contain n-1 vertices. And if it does, the depth of this recursion becomes n. And so we're not really making enough progress to get a linear time algorithm. Okay. So next, let's make one final push to obtain our linear time algorithm. So let me show you what the final algorithm will do in pictures. So the idea will still be to use all of the ideas we've discussed so far. We just need to arrange them in a different way. So we'll start with the entire space, and if there is a vertex that has a small ball around it, then we'll sample a small ball. And then we'll recurse within that small ball and do something, find a potential function. And then we'll go on to the next vertex, which has a small ball around it. And we'll again sample a small ball around that and recurse and find a potential function that works within that ball. In this way, we'll cover all of the vertices that have small balls around them by random balls and recursively compute potential functions that work for the balls within those random balls. And finally, we'll also compute a potential function that works for the entire leftover space. Okay, because the leftover space consists of vertices that have large balls. So we'll end up with a whole bunch of potential functions. We'll then combine all of these potential functions to obtain one single potential function, which handles almost all of the edges in the picture except for those edges that cross the boundary of the ball in the wrong direction. Okay. And finally, we'll resolve the edges that cross in the wrong direction by a single run of the BFD algorithm. That's the high-level picture. So here's a description of the algorithm. So as I said, as before, we pick k random vertices or log n random vertices and use them to estimate the distances to all the other vertices, the non-negative distances to all the other vertices. And then we simply run over every vertex, and if the vertex has a feature that its ball of radius delta over 4 contains less than 0.6 fraction of the q's, we pick a random ball around this vertex. Now, before we were picking the radius of the ball uniformly at random. But to make the analysis work, now that we have so many balls operating together, we need to pick the radius of the ball in a careful way so that we can avoid a very wasteful union bound over all the different balls. And it turns out the right thing to do is use the geometric distribution to pick the radius of the balls. So what does that mean? We'll toss a coin that is heads with probability order log n divided by delta until you see the first heads. And R will be the random variable which denotes the number of coin tosses until you see the first heads. This is how you sample R. Then we have a counter J, and using the first ball, we'll take the ball of radius R and use it to define a subgraph G1. Okay, So Gj will be the graph supported on the current ball minus all of the graphs that we partitioned off from the space before. And then we recursively compute a potential function phi that works for this Gj and label all the vertices to indicate that they belong to this graph Gj. Okay. So in this way, we cover the entire space with graphs for which we compute potential functions. And finally, we compute the graph Gj plus 1, that's the leftover vertices, all the vertices that have large balls around them. And we compute, recursively compute a potential function phi plus 1 for that graph. Okay. So that gives you potential functions for all of the vertices in the graph. Then we go back through the entire picture and fix all of the edges that crossed between these graphs in the right direction. So for I going from j to 1, you look at if gi is labeled I forward, that means the edges that go in the right direction are these ones. They're the edges going from the future graphs in the picture into gi. And we can shift phi I, the potential function for the ith graph by some constant to fix all of these edges. Similarly, if gi is was made by looking at a reverse ball, then we can fix phi I in a different way, okay, to handle edges going in the opposite direction. So once we've found the potential function that fixes all of those edges, we run BFD on the remaining graph and the potential function we have so far to fix all of the remaining edges, the edges that went in the wrong direction across the boundaries of these graphs GI. So that's a very high-level description of the algorithm, and that's the level of detail I'll use here, except I'll make a few more comments about how to handle the details. First of all, how do you do this efficiently? You know, how do you actually compute these balls and these graphs efficiently? Well, you want to run Dijkstra's algorithm, but you want to be careful. So a nice way to do it is to initialize, you know, before the algorithm starts, initialize the heap that will be used for Dijkstra's algorithm with all distances set to infinity. And the first time you encounter trying to find this ball, what you do is you run Dijkstra's algorithm to find this ball. Okay, so you run Dijkstra's algorithm with this vertex u set as the start vertex. So you set its d value to be 0, and run Dijkstra's algorithm to find the vertices in the radius delta over 4. Once you've identified all of those vertices, you take them out and construct the graph, the first graph. And now you want to reset the d values of all the vertices that are outside that graph to be infinity, to restore the heap. Okay. The key point is you don't want to spend order m time to fix the heap up. You just want to spend time that's proportional to the size of the current graph that you're working with to restore the heap. But that can be done. Okay. Once you find the vertices you're working with, you take them out and you restore the heap by just looking at the edges that come out of that graph and cross, okay, and fix the d values in the heap in that way. So that only takes time that's proportional to the size of the graph that you're working with in this step. Okay, second point is, why do we use a strange distribution on the radius of the ball? Well, this choice of distribution has two features. First of all, the probability that the radius exceeds delta over 4 is extremely small. Okay, that's just a calculation. It's because, you know, the way the parameters have been set, the probability that you see that many delta over 4 tails is exactly this number, which is exponentially small in log n. It's like n to the minus 10. Okay, so it's very unlikely that you'll see r be more than delta over 4. On the other hand, for every edge xy, the probability that at some point in this algorithm x is covered by a ball one of the random balls you picked, but y is excluded from the ball, that can be bounded. That's because condition on x being inside the ball, the geometric distribution has the property that means that there's some number of tails that we've seen that's enough to cover x. So the radius has just covered x. And now we're worried about the event that that we'll see a heads before y is also covered. But the probability of that event can be bounded by this formula. Very similar to the analysis we saw before, because the y belongs to a ball of just slightly bigger radius. Okay. So just by the union bound, you get an upper bound of this type on the probability that y is not in the ball, given that x is not in the ball. And this means that even though there are many balls in this picture, for each edge xy, we just need to look at the event the first time that x is covered by a ball. What's the probability that y is not covered? And that probability is small. And that eventually says that the bound you get here says that in expectation, the parameter eta v that we were working with before, the number of negative edges on the shortest path from S to v, is typically bounded by log n. The expected value is log n. And that means that the expected running time of BFT at the end here is almost linear. Okay, so this algorithm runs in expectation in almost linear time. Finally, to bound the entire running time of the algorithm, you see we have an algorithm here where the amount of work done in a single recursive call is almost linear. And there are two kinds of recursive calls. The first one here works on a graph whose vertices are smaller, the number of vertices is smaller by a constant factor. And the second kind of recursive call that you have, we claim, works on a graph where the parameter delta reduces by a constant factor. Okay, and that's because that's very similar to the lemma that we saw before. If you're considering the graph gj plus 1, now inside gj plus 1, all of the balls around vertices are large within the graph G. Okay, and that means if you have a SV path in gj plus 1, that's the shortest path, that might look like this red path here, then there's a blue path possibly going in G. Right? This blue path might be a path in G and not in gj plus 1. But that's not a problem. You still obtain a cycle here whose total weight is at most delta. Actually, it's whose total weight in our application is delta over 2, right? Because we had balls of radius delta over 4. And that means the number of edges that you encounter here is bounded by delta over 2, roughly. Okay, so you obtain that this recursive call reduces the parameter delta by a constant factor. So that means you have an algorithm which is almost linear time. In every recursive level, the amount of work is almost linear, and the depth of the recursion is only polylogarithmic in the parameters. So that gives you overall an almost linear time algorithm. Okay, so I know that was quite a complicated analysis, and it's not as simple as some of the basic classic algorithms we saw before, but it's the first progress on this problem in many years. So I think it's really amazing. Now in this video, like in all my videos, I did not mention the people who came up with these amazing ideas, but if you look at the description of the video, you will find links to all the references, which contains a detailed account of the history and gives credit to the right people for coming up with these ideas.